there. That tells us we have reflectional symmetry. And then rotational symmetry. Again, rotational, it cannot be 360, can it? The way that's defined, it has to be less than 360. And really the biggest turn you'll have is 180 degrees, okay? It's going to be up to 180, all right? That's what we found out last week on rotational symmetry. So if there's reflectional symmetry in there, great. It could be one line, it could be more than one line. It just depends on the situation at hand. So let's do this. We got to square up the circle. Do we have any reflectional in there? Sure do, right? And on that reflectional symmetry right there, you say we do. And where is our reflectional symmetry happening? Vertical, yep. Where else? Horizontal, yep. And the two diagonals. One diagonal and two diagonals, okay? Our IDs make that a little bit nicer maybe than freehanding it, but I'm not going to be that picky or anything like that, okay? Mentally erase those reflectional lines of symmetry, kind of start fresh, and then ask yourself, is there rotational happening in there? Is there rotational happening in there? Definitely. Now, when we say rotational, I am always asking them for what is the minimal turn? What is the minimal degree? Because whatever that minimal degree is, then we can do multiples of that, right? So what is that minimum degree to turn it on to itself? 90 degrees, right? If you were to take that in patty papers or buddy, okay, patty papers or buddy, if you're not seeing it, you can always use that patty paper. Quiz and test next week will be it. But a turn, and what's our direction, our default? Counterclockwise. So we can turn that, and I'm looking for that turn. Okay, if you don't tell me which way to turn it, I always can assume you're going to go counterclockwise. Okay, if you're telling me to go clockwise, then you will tell me like a CW at the end for clockwise, but if you don't tell me anything, we always default to counter. Okay, cool. All right, real quick, offside. The next one, any reflections up there? What we got? And going right down the middles, correct. Flip, flip, cool. Any rotationals happening? What's our rotational degree? Yeah, this one is going to be exactly a 180 degree turn. That's the minimum that we can do, where it lands on itself, and that's it. Okay. Let's go with the next one here. Letter C. Any lines of reflection happening? This is where we kind of start off with. You should be fairly symmetrical. If we were to cut Eva right down the line vertically, that would be a shame. Okay, it'd be messy too. If we were then to fold her along lines, she should be roughly symmetrical. And in this one, this case, right there. Anything else? No, I don't think there's anything else, is there? Any rotational happening off of that? No. And if you say no, the common mistake I see a handful of kids do is say no and then they put a 360 on there. Don't, okay? If you say no, what are you going to do? Leave it blank, or put a line through it, or say not NA for not applicable at the minimum. But don't put me a number in there. If you put me a number in there, that's not what we're asking for. We're looking for you to realize there is no turn happening in that, okay? Okay, cool. And then the last one, is there any reflectional happening in that one?
Yes.
Yeah, it's not vertical, not horizontal. What is it? We got a diagonal happening, right? So on that diagonal, I see a diagonal like that, right? Kind of going through there. And do we have another diagonal happening? I think so. I think like that too, don't we? So there's not just one, but there is two. And for me, it wasn't I should say obvious, but maybe it wasn't as obvious because our eyes always go back to vertical and horizontals. But don't forget about those diagonals. And again, patty paper is nice. You could fold it over that patty paper, draw it on there, put that patty paper, and see where that might happen out. So I think 2 lines, is that correct? Yeah. 2 lines? 2 lines of symmetry happening in there, okay? Reset yourself. Again, patty paper might be nice for the rotational. Is there rotational happening on here? Excuse me, I think there might be. Okay, what would be that degree of rotation here? And the thing that would be kind of maybe messing with your minds a little bit is that diagonal right here. So this would be what, a 90-degree rotation? So not quite the same. But then turn another 90 and what do we get? 100, 180 when it lands on itself, right? So what do we have? Yes, we do. And what would it be? It would be a 180. Again, if you're not 100% sure, patty paper is your buddy, and check with the patty paper, okay? So that's what we kind of did last week, right? That's what we did a little bit on Friday with reflection and rotational. And we did that, and we flipped it as you did. And we then talked a little bit more about, we talked a little bit about regular polygons, and we're going to do a little bit more work with that here today with the regular polygons. And I kept saying the word regular polygons. Let's talk a little more about that. To be regular, now, it doesn't have to be, sorry, let me rephrase this. A hexagon or a pentagon doesn't have to be nice looking like we have here, okay? Here we got a, what? 1, 2, 3, 4, 5. It's a hexagon, right? This doesn't have to be a nice looking hexagon. As long as it has 6 sides. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. That's a hexagon. But for the most part, those types of hexagons we don't do much with because it is not much we can do with an irregular hexagon. Okay, where things happen most often is when it's nice looking. It's regular. So what we tend to work with is what we have on this page, are regular polygons. So regular polygon has our center. And what do we know about the sides and angles then? You all told me on Friday they were what? They're the same. They were all equal. Equal sides and also equal angles. So to be regular, like you said, they were equal sides and equal angles. And what then happens that we started doing is we started dividing it up into some equal, we didn't necessarily say triangles per se. We were talking about the center, we were talking about angles. But we're creating a bunch of particular triangles, okay? So from that center here, these, again, from that center to each vertex, these are, again, what we call a radius, okay? Just think about like a circle. And these are all congruent. So if we look at this triangle right here, well, what type of triangle are we creating then? Okay, I heard equilateral, I heard isosceles. It almost is, it depends on the shape, but it for sure is isosceles, okay? It for sure is going to be isosceles. And the other thing about this is, what's going to also be true about all these triangles that are going to be here? Yeah, down here, this is a what? This is an octagon. We get all of these isosceles triangles being created. You're creating a whole bunch of isosceles triangles. And they're not just any old isosceles triangles, they're all the same isosceles triangle. We agree in agreement with that. So what we're doing is creating a whole bunch of congruent isosceles triangles. And again, kind of go back thinking about maybe a pizza, depending on who's working that night, I guess, at Papa John's, Little Caesars, wherever. Probably not Emo's, because Emo's is the square beyond compare, right? So they cut theirs into squares. But let's go back to triangles, I guess. All right. But what we're creating here is a whole bunch of congruent isosceles triangles. So in that, they're all equals, right? Now, from there, that goes then to what we say is a central angle. That's what we did on Friday. Right around that center, okay, that's where we're at. And how do we talk about finding, right there, we want to know the measure of that central angle, that single central angle. So around that center is 360 degrees. So 360 degrees divided by however many angles are right there. All right, however many triangles are meeting at that center. In this case, because this one is a hexagon, yeah, 360 divided by 6. It's equal to the number of sides. So what that means is, right here at the center, we have a whole bunch of equal 60 degrees, don't we? Now you don't have to put 60, 60, 60 in there. Just realize each central angle is 60 degrees. So if we were to take our patty paper, trace this on there, and turn it 60 degrees, it lands on itself, doesn't it? That's what we were at. So now let's do an answer on our question, okay? This does have rotational symmetry. The rotational symmetry for that hexagon, this regular hexagon, is 60 degrees then. Now we can go about answering it out. What is the image of B for a 240 degree rotation about M? Doesn't tell you the direction, so what's our default direction? Counterclockwise. So go find B. You got to know what 240 is. How many turns are we doing? 4 turns, right? It's 240 divided by 60. It's 4 turns. So B, 1, 2, 3, 4. B is going to be where? Correct. It's going to land on point D. That's it. Okay. Same deal. Name F, but watch very carefully. This time they do tell us direction to go. What direction do they tell us to go this time? Clockwise. The biggest mistake I see students do is not read carefully. All right? 6 degrees clockwise. I'm not saying these are easy questions, but this time of the game, they should not at all be too bad, but they don't read carefully. So what are we doing? F clockwise. So it's either going to be E or A. That's just one turn. So which one is it? A. Okay. And we can do the same thing for the segment. Doesn't matter if we're doing a point or a segment. Just make sure you know which direction you're going and how many turns is that going to represent. So 180 degrees counterclockwise. CD, where's goes find CD at? Right here is CD. 180 degrees counterclockwise. So which way am I going? Towards BC or towards DE? BC, right. So how many turns is 180? 3. 1, 2, 3. So what do you land on? I'm sorry? FA, right? FA? That's it. Okay? So that's all we're doing. That's all we're doing. Just make sure you know which way you're turning, how many turns, and tell me where you land. Nothing too crazy off that. Same deal for the regular octagon, but you got to know how many turns is a regular octagon. It's got rotational symmetry, absolutely. But what is that degree turn on that regular octagon? What is that regular turn? 360 always, right around that center. Divided by how many? Yeah. How many are right there around the center? It's always going to be equal to the number of sides. So 360 divided by 8 is 45 degrees. So one turn of this is 45 degrees, correct. So keep that in mind. We now know what our rotational symmetry is, 45 degrees. Cool. All right, for that first one, they don't tell us how to rotate, so our default is counterclockwise. What's a 135? How many turns? 3. And if you're not sure, we always get our good old handy dandy calculator. Okay, 135 divided by 45 means, correct, 3 turns. So 3 turns of A. Where's A at? Right there. 1, 2, and 3. So what are we at? Round point F, aren't we? Make sure you go the right direction. Same deal, DE. Take that segment, DE. Now it says clockwise this time. Again, 270. 270, now 135 was 3. 270 is double to that. So it should be 6. But if you're not sure, you get a calculator. 270 divided by 45 is 6. So where's DE at? We're going 6. So we're going to go what? 1, 2, 3, 4, 5, and we on BC, CB. Either one's fine. I'll take either one there. Okay. Just make sure you go the right directions, guys. Those are the dumb mistakes happen. And the last one, counterclockwise. It does say counterclockwise. We know 135 is 3. Finish off. B, about O. B, counterclockwise, about O. 1, 2, 3. Somebody get what? There you go. Nothing crazy. Now, later on, we're going to continue doing this. I asked you at some point throughout this year, how do you find the area of a square? And we said the area of a square is what? Side squared. Area of a rectangle we said was base times height. And then I asked you, hey, what's the area of a triangle? You guys said 1/2 base times height. Then I asked you, hey, how do you find the area of a pentagon? Nobody knew, right? An area of a hexagon. Why would you know that? But now we're going to keep building off of this. How do we find the area of an octagon? Don't know. But now we've been building towards this. What do we say we have here? Congruent isosceles triangles, right? How many do we have in here? How do you find the area of a triangle? So we're going to keep building off this idea of regular polygons. You know how to find the area of a triangle, right? 1/2 base times height. If I can find the area of one triangle, I can find them all, right? One triangle times how many here? So we got that idea we're building on. Area of one triangle times 8. So that's what we're going to start doing as we work throughout the school year. We're going to come back to these polygons, and you've got this idea of breaking it down to smaller shapes, right? We've been doing that, so we're going to keep building on that. Okay, let's go around. All right, as we're talking about polygons really quick, let's make sure we know our names of our shapes. That sounds silly, but number of sides and the name. Number of sides, 3-sided figure is called a 4-sided is called a what? Caden? We get a bunch of 4-sideds out there. In general, it's called a quadrilateral because we also have a rhombus, right? And we also have a trapezoid, right? And we also have a kite, right? So in general, though, we have ourselves quadrilaterals. I know that's the tricky one every year. 5-sided is a pentagon. 6 is a. All right, here's the one that goes either way. So yeah, 7 is the one a lot of students don't remember. 7. What did you say? Okay, septagon is just fine. That is one name for it. There is another name out there for it. Anybody remember the other name? That's no big deal. Heptagon. Heptagon is the other name for a 7-gon, for a 7-sided figure. 8-sided figure is a octagon. All right, 9 is hit or miss. There's always at least a couple people that maybe know a 9. Or not. Okay. It's called a nonagon. 9 is a nonagon. Alright. 10, I got usually a few people. 10 is a decagon. Okay. Decagon. Okay. Now these are the ones you should know your names of. That's what they tend to use is in words. Okay. The name of it. The other common one that happens quite a bit, it's nice and divisible into 360, is a 12-gon. Remember the name of a 12-gon? Dodecagon. That is correct. Dodecagon happens out quite a bit. It's because it is divisible into 360, so it does happen out quite a bit. Those are the ones that you should know the names of. After that, we just say an n-gon, the number of sides. So a 13-gon, a 14-gon. They have special names, but we don't care. Okay, 100-gon and so on. So we're going to do more work with these regular polygons throughout, but that's where we're at. Okay, last one, we'll call it. Take a minute. I want you to take these figures and check all that apply. Now, every year I got to go through this one though. Whenever you get to the rotational part of things, like we've been doing with the reflectionals, imagine that line is not there anymore. Can you rotate that? It lands on itself. Okay, so the line's there for the reflection question. Imagine them erasing that line. Is the rotation happening there? Okay, I'm going to give you a minute, go through, cross those 3 rows, select all that apply that are happening there. So go through those figures 1, 2, and 3, see what you can do, select all that apply. ACT type of questions. All right. First off, the reflectionals. Let's just go down vertically here. Do we have reflectionals? Let's get those out of the way. Does figure 1 right here, is that reflection working?
Yep.
Okay. Figure 2, is that reflection working?
Yep.
Look very closely on this one.
Yep.
Is that reflection working on this one?
Yep.
Yeah, it is. It does appear to be working. If you're not sure, what can we always check with? I believe it is working. Okay, before I go through and do anything to rotations, first thing I'm going to do is calculate the 3 rotational symmetries. So on this one here, it's a square. It shouldn't have to necessarily do it, but when we were doing the regular polygons up top there's a hexagon for 6 sides, an octagon for 8 sides. It sounds weird, but what's the regular polygon for a quadrilateral?
Actually, sorry, I'm going back to figure 3. That line's not in the corner exactly.
I hear you, and I would take either one.
I didn't know
Yeah.
if you were gonna.
No, I know what you're saying there, Carter. I would go with whoever consensus was there. Okay, so what is the regular figure for a quadrilateral? There's a whole bunch of options for quadrilateral. You all told me that a few minutes ago. The square is the regular figure for a quadrilateral because the square is all congruent sides and all congruent angles, right? Now we know the turn for a square is 90 degrees, and the way that's happening is 360 divided by 4. So its rotational symmetry is, we said 90 because of that. In a triangle, 360 divided by what? 3. It's a regular. 360 divided by 3. So what's its rotational symmetry? 120. And what shape do we have here? What is it? 1, 2, 3, 4, 5, 6, 7, and it's an octagon. So 360 divided by 8 is 45. So with that octagon, that triangle, and that square, I'm looking for turns of 90, 120, and 45. So before we go and answer these out, this better not be anything checked. If anybody put a 60 on there, go erase it. All right, I see some erasing going on. Okay, because I can't, those are my minimum turns, right? I can't go anything at a 60-degree turn. That 120 is where students usually kind of screw that one up, okay? So, does anything up here have a 45-degree rotation? The octagon does, right? Now, whoops, sorry, let me back that up. Because we're on figure 1 here, aren't we? So figure 1 is not happening, is it? 45-degree turn does not work. Does a 60-degree? Nope. It's got to be a 90 and multiples of 90. So that is happening. And does a 120 work? Multiples of 90 and then a 180 works. Okay. Figure 2. Figure 2 has to be 120 and then multiples of 120. So figure 2, definitely not. But this is the one I see too many people go ahead and select because 120 is 60. I see why that happens, but not happening. So 90, nope. 120, and that's it. And then lastly, figure 3 is a 45. So 45 for sure. 60, that's not a multiple. 90, it is. 120, is that a multiple? Nope. Is 180? There you go. Okay. So anytime I see these, go calculate those rotational symmetry or those rotational degrees. Okay. All right. That's where we'll pause it.